Electron configuration of an atom. Electron configuration is the arrangement of electron around the nucleus. So here we have the S, P, D and F letters. The different sections of the periodic table are very important in understanding the electron configuration of an atom. The modern periodic table was built using 4 blocks. These blocks are S block, P block, D block, and F block. What do S, P, D, and F mean? These letters refers to the sublevel within the principal quantum level n. So for n is equals to 1, there is only one sublevel. That sublevel is S sublevel. If we have n is equals to, there are 2 sublevels, S and P. And again, if we have n is 3, there are 3 sublevels. These sublevels are S, P, and D. So within each sublevel, there are n sublevels. Okay, in each level, there are n sublevels. Okay. Do you know, this is the sample of modern periodic table, and we can see the 4 blocks. On the left side, which indicated by pink color, indicates S block, starting from 1, just vertically. Do you see? 1s, 2s, 3s, 4s, 5s, 6s, and 7s. On the right side, there is green color, which is represent P block elements, and between S block and P block there is D block elements, which is transition block. Okay, and the other block is F block elements. F block elements represented by strong green, as you observe here. An example, we can have arsenic atom. Okay, if you remember, the electron configuration for arsenic will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p3. The first number is which row it is in, or the principal quantum number, or energy level. The character is the block in it, which refers to the sublevel. The superscript is the total number of electrons in the sublevel. In short, you can remember how to put the electron configuration of an atom in each sublevel. The diagonal rule. First, we have to put 1s, the next 2s, 2p, 3s, 3p, 3d, 3 times, 4s, 4p, 4d, 5, 4f, 4 times, 5s, 5p, 5d, 5f, 5g, 6s, 6p, 6d, 6f, 6g, 6h, 7s, 7p, 7d, 7f, 7g, 7h, 7i. So, first we have to put electrons in 1s sublevel, and then in 2s, and the next 2p and 3s. Then after 3p, 4s, then 3d, 4p, 5s, and again 4d, 5p, 6s. Then after we have to put electrons after 6s, 4f, 5d, 6p, 7s. After 7s, we have to put electrons in the sublevel 5f, 6d, and 7p. Then after 5g, 6f, 7d. These do not exist in normal ground state electron configuration. Therefore, we have to use this sequence. D4 and D9 rules. You have to remember these rules. Sometimes an electron configuration will end with 4 or 9 electrons in D sublevel. These are unstable, so we have to change into stable form. We'll steal electron from the S sublevel before it to stabilize. For example, chromium atom. The expected electron configuration for chromium atom will be 1s2s2 2p6 3s2 3p6 4s2 3d4. Do you see? There is 3d4. 3d4 is unstable. It is unfilled. It is not also half filled, but it is unfilled. Therefore, we have to convert into stable electron configuration. So 1s2s2 p6 3s2 3p6 4s1 and 3d10 is the stable electron configuration for chromium. And the answer is C lever. If you see the electron configuration for C lever atom, it ends with 4d9. D9 is unfilled, so it is unstable. Therefore, we have to convert into stable form. Just we can jump 1 electrons from 5s to 4d9. Therefore, it becomes 5s1 4d10. So it's now stable. The other thing that we remember in the electron configuration is noble gas electron configuration. In a obvious solution and convenient shortcut, okay? Noble gas electron configuration. The noble gases are, as you know, helium, neon, argon, krypton, xenon, and note that each noble gas finishes a row or energy level. Noble gas configuration takes advantage of this by condensing what you have to write. For example, helium is 1s2 simply. Carbon, we can write the electron configuration for carbon using noble gas electron configuration. Therefore, carbon has 6 electrons. The noble gas electron configuration for carbon atom will be helium 2s2 2p2. The other example, normal electron configuration for arsenic. Look, it is so huge, so we can make it short. 1s2 2p6 raised to 3p6 represents 8 electrons. The noble gas with 18 electrons is argon. Therefore, we can put the electron configuration for arsenic shortly: argon 4s2 3d10 4p3, like this. Okay, do you see? Argon 4s2 3d10 4p3. It cuts down on a lot of writing, and that is a good thing. The other is orbital diagram. They are useful. So orbitals. Each sublevel SPDF contains orbital. Remember, orbitals are electron clouds that hold the electron, 90% of them. Each orbital can hold 2 electrons. So S orbital can hold 2 electrons. That's one orbital. P, 6 electrons will be there because of the existence of 3 orbitals. D, 10 electrons will be there due to the presence of 5 orbitals. F, 14 electrons can be there due to the presence of 7 orbitals. Here is the principle, the Bohr principle. Each electron occupies the lowest energy level orbital. Electrons are lazy. All orbitals related to an energy level are of equal energy. For example, the 3 2p orbitals are the same in energy, so they are known as degenerate orbitals. The other principle, very important principle, is Pauli's exclusion principle. As you observe, a maximum of 2 electrons may occupy a single orbital, but only if the electron have opposite spin. The electron should be put in opposite spin. The spin electron has an associated with the spin either one way or the other, like a top. These spin are called spin up and spin down. So example on board Hundus rule. You can see the nitrogen atom 1s2 to p3. Okay, we have to put the spin of each electron in opposite side, and if there is orbitals having the same energy, first we have to put all the given electrons single in the same spin, not in the second one, okay, not this one, but this one is. The order of things. Electrons being unfriendly fill up the empty orbital before sharing orbitals, similar to sit on a bus. On a bus, you sit alone rather than with a stranger if there is an option. And the other very important thing is the shape of the orbitals, sp and d orbitals. Sketch this shape, please. S orbital has spherical shape, but p orbital has dimple shape, and again the shape of d orbital is double dimple. If you look from this figure, the shape of d orbital is more complex than that of the shape of p orbital, and again you can look the shape of f orbitals, more complex, but don't bother yourself for the shape of orbitals. Please write this at the bottom of your outline. Orbital there on the left side is orbital, shape spherical, number of boxes or orbitals is 1. For P, double dimple shape, and 3 degenerate orbital will be there. D, double figure 1, double dimple, 5 orbitals will be there. F, don't worry. What is an ion? Example of ion: sodium plus, magnesium 2 plus, iron 3 plus, chlorine minus, sulfur 2 minus. When writing electron configuration or orbital diagram for ion, it is little harder because it can look like different ion. Just subtract the minusing electron or add the extra electron highest energy level. So, for example, if we have lithium 2 plus, its electron configuration will be 1s2, 2s0, because totally lithium atom has 3 electrons, but it has lost 1 electron, therefore we can have only 2 electrons. We have to put the remaining electrons in its electron configuration using 1s2 only. And the other is sodium plus. This ion indicates that sodium atom lost 1 electrons. As you know, totally sodium atom has 11 electrons, but after it has been lost 1 electron, it will have only 10 electrons. Therefore, its electron configuration will be 1s2s2 to p6, and for others the same thing will be described.